Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I'm dealing with thermodynamics, and in this topic this is lecture number 25. Well, in this lecture I will explain you the relationship between Cp and Cv. You know that Cp is heat capacity at constant pressure. This is a condition. Without condition we cannot explain heat capacity, and Cv is heat capacity at constant volume. Okay, so now we can say that it is clear that two heat capacities Cp and Cv are not equal. Normally we found that Cp is greater than Cv by a factor which is related to the work done. So, and one more thing, that heat capacity is not a state function. That means heat capacity depends on the path through which we carry the process. So it is not a state function. Now we'll see at constant pressure, we can say that part of heat absorbed by the system is used up in increasing the internal energy E of the system, and other parts for doing work by the system. So this way total heat which is absorbed is used in two different processes. One for increasing internal energy, and part of that is also work done by the system. Now we'll see at constant pressure, now we see at constant volume. The whole of heat absorbed is utilized in increasing temperature only. So we can increase temperature in case of Cv of the system. As there is no work done because there is no change in volume by the system. So there is no work done by the system at constant volume. Okay. Thus, increase in temperature of the system would be lesser at constant pressure than at constant volume. Therefore, we can say that Cp is always greater than Cv. Now you know that Cp is equal to dH by dt and Cv is equal to dE by dt. Okay, and enthalpy's equation is H is equal to E plus PV. For 1 mole of ideal gas, PV is equal to RT. So substitute this value over here. So we write H is equal to E plus RT. Now differentiating the above equation, with respect to T, then we write dH by dt is equal to dE by dt plus R, and dH upon dt is equal to Cp, dE upon dt is equal to Cv plus R. So Cp is equal to Cv plus R. Therefore, Cp minus Cv is equal to R. Okay, so this is the equation or formula or relation between Cp and Cv. Okay. Now we will see the relation of heat capacity when expansion of gas takes place in vacuum. So this is a new topic, expansion of gas in vacuum. This we have already discussed, but once again, suppose a gas is filled in this cylinder. This is a piston which is kept over here. Here we apply pressure P external, but in vacuum P external will be 0 because expansion takes place in vacuum. So if gas is expanding in vacuum, that is P external will be 0, then piston move automatically upward without any effort. Therefore, we can say that, and you know that work is W is equal to V1 to V2 P external dV, and as P external is 0, work is 0. So W will be 0. Okay. So when gas is expanding in vacuum, no work is done. No work is done. No heat changes, therefore dQ will be 0, dW will be 0, and therefore internal energy change is also 0. Okay. Now we will see internal energy U. It is a function of temperature and volume, and for that we write du is equal to du upon dt into dt at constant volume plus du upon dv into dv at constant temperature. So we write du is equal to cv dt plus du upon dv into dv at constant temperature. As du is equal to 0 for vacuum, and therefore 0 is equal to cv dt plus du upon dv into dv at constant temperature. Okay. Now we change the side, so minus cv dt is equal to du upon dv into dv at constant temperature. Now change the side of dv over here. So we write du upon dv at constant temperature is equal to minus cv into dt upon dv at constant internal energy. Okay. So this can be an expression of work or internal energy change when, or heat capacity when expansion of gas takes place in vacuum. That's it in this lecture. Thank you so much.